Hi, I'm Marty Woodle. I'm a retired mechanical engineer from Brookhaven National Lab, and I'm going to talk to you a little bit today about our bridge contest. We have two pieces of pine here simulating bridges. The bottom piece, from the arrows you can see that the grain is oriented across the span of a simulated bridge. The upper piece is also pine, but the grain is oriented perpendicular to the span of the bridge. We're going to demonstrate the difference in strength of the wood in these two different directions. So we've got the two bridges set up on supports, and I'm going to step on them. I weigh about 185 pounds. Well, I had a big supper, maybe 188 pounds. I'm stepping first on the bridge where the grain is oriented across the span. I'm now going to step on the bridge. As you can see, the second piece with the grain oriented perpendicular to the span is much weaker. The wood is much weaker and failed very easily. I didn't only put the weight of 1 foot on that. So what happened here is that when I stepped on the wood, it wanted to bend like that. So it stretched out the bottom piece of the bottom fibers of the wood and tried to compress the top, and it was not strong enough to resist it. As in this case, the same thing happened, except that since the grain is running this way, it is much stronger and resisted the stresses on the bottom and the top of the bridge. So when you design your bridge, you want to design your bridge so that the loads travel in the direction of the wood grain. All right, I'd like to talk a little bit about the stresses in bridges. There's basically three kinds of stresses that we deal with: tension, compression, and shear. In tension, we are taking a structural member like this, and basically I'm trying to pull it apart. And as you can see, not much happens, and as long as I'm not strong enough to pull it apart and break, that means the tensile member is working fine. Now, something entirely different happens when you put compression on a structural member. And I've set up a little device here to show what happens. We have here a rather thin rod. It's a 1/16 of an inch in diameter. And what I'm going to do is I'm going to initially apply a load on it. Now, if you look down at the dial, you can see the dial move when I apply the load. All right, I applied the load. You'll notice the dial didn't move very much because I couldn't apply much load, and look what happened to the member. It bent, and in the engineering that's called buckling, and it's a stability failure. So what do you do about that? Because actually, top members of the bridge will be in compression, and you'll have to design to avoid this happening. So what we're going to do is I'm going to enlist the help of Dan here, and he's going to move a brace down here, which is halfway, which divides us into two sections. Now he's going to hold that rigidly so it can't move side to side, but it allows the rod to move freely through it. So now I'm going to apply the load. Watch the dial. You'll notice that we got a significant more load on it now, but look at the rod. It's buckling between the two places here. All right, I'm going to release the load, and now we're going to brace the load from the side in two places to divide it into three pieces. Now, and I'm going to apply the compressive load, and you notice it's even more, but you see it's buckling in all three places. So what this shows you is that thank you, Dan, that in bridge construction, you have to be able, in your design, to brace the members that are in compression, and typically the top surface, the top members of the bridge will be in compression. So they have to be braced to keep from buckling. Now, a little bit more about buckling. If you look at the end, the cross-section of this, it's round, and it's perfectly the same amount of material in every direction from the center, which means that we don't know which way it's going to buckle. It will buckle in any direction it wants. It could go that way, it could go that way. Now let's take another member that could be used for a structural member. And I've just got a yardstick here. Now if you look at the end of the yardstick, it's a rectangle. And in the width direction, it's much more material than in the thickness direction. So when you put a compressive load on that, this will tend to buckle only in one or two directions, that way or that way, because it's too stiff and too much material here, which will keep it from buckling. So I'm going to demonstrate that. I'm not going to put it on the scale, but I pressed it, and it could equally go that way. But it can't go this way. It's going to go in the weak direction. So that's another thing. And if you have a top structural member in it, you could keep it from buckling by making it wider in one direction and bracing it in the other direction. So again, that's another structural tip to keep in mind when you're designing your bridge, particularly the top surface of the bridge, the top structural members, which will be in compression. Now we're going to talk about shear strength. Now shear strength, or shear stress, is a strange type of stress, but it's very, very important in bridge design. We're going to look at a typical joint in a bridge. I've drawn a kind of a generic bridge here, and we're going to look at this joint A. And this is a vertical member coming down to join the bottom member of the bridge. And you'll remember I said before that the top member here is in compression, but the bottom member of the bridge will be in tension. So we're going to go over here, and I'm going to show one type of joint. This is A1. And this is, we call this a butt joint. And we don't call it a butt joint because it's no good. It's just called a butt joint because it's butted up against the member. This represents the bottom tensile member here, and this is the vertical member coming down. And if the vertical member is in tension, this of course will be in tension, what's going to happen is the glue joint is this little square at the bottom. Now what's going to happen, remember from our previous talk about the grain, you have the grain running this way, so now we have a piece of wood glued to it pulling across the grain. And as we remember, across the grain is the weak section of wood. And what's going to happen probably is, generally speaking, glue is stronger than the wood, so what's happened is going to pull out a section, or rip out a section of wood here and fail. So how do we get around that? Okay. A2 is an alternate design for this. Instead of being a butt connection, it's actually attached to the side, a shear, it's called a single shear joint. And you see now we have an area of glue here that is going to be pulling to the side. It's not going to be pulling across the grain, but it's quite a bit stronger than this joint here, because you've got the whole area of glue here that is acting, and actually it turns out that the glue also is probably stronger than the wood, but still it's less likely to fail under the load. Finally, we have something called double shear, which is the best joint for this particular member. And what happens is, we've taken the original piece of wood that was butted, and we put two short pieces on either side. And this is called double shear because you have two pieces here. You may put glue on the butt joint, but you also have glue here and on the back side of it, which is the best and strongest joint for this type of structural connection. Okay, I wanted to give you a few ideas about how to actually fabricate your bridge. And one of the traditional ways to do it is to use a piece of foam board, which you can get at Staples or any other, or Hobby Lobby probably. And what you do is on a piece of paper, graph paper, you make your drawing of your bridge, the side of the bridge, and you make it full size to the exact scale, the exact size that you want the bridge to be, showing all the members and how long they are and where they meet up. And then what you do, and you tape it to your foam board. Then you take a piece of wax paper, I guess everybody still has some wax paper, and you put it down over it, and you can see through the wax paper to see the design underneath. And the reason for the wax paper is that you're going to make glue joints, and you'll be able to lay your wood and cut it to length and lay it on here and make the glue joints, and the glue won't stick to the wax on the wax paper. And the way you secure the wood is you use T-pins. I don't know if you can see the focus on the T-pins. And basically, you set the wood, I'm just going to set the wood here, I'm not looking at it, and you put the T-pins. You do not stick the T-pins through the wood. That will destroy the wood. But you put the T-pins on opposite sides of the wood and tension them so that they won't, so that the wood is held into place. And remember, this will be flat, so the weight of the wood will hold it down. And then you match your other pieces up to it, glue them, and use pins on all the other pieces to hold it together. Let it dry. When it dries, you can pull the pins out and pull out your constructed bridge side. And you can do the same for both, so both sides of the bridge come out to be matching and symmetrical. The next thing you would do is you would have to fabricate the cross pieces to tie the two sides together, but that you can figure out pretty straightforwardly.